We start with a completely bare, unpowered motherboard. No memory, no storage, no power supply. Just the silicon and copper routing waiting to be utilized. Watch what happens when we lock a high-performance CPU into the socket and attempt to boot. Instantly, the board throws warning indicators for power, thermals, and memory. The system halts. A modern central processing unit is capable of executing billions of instructions per second, but it is a strictly dependent processor. It cannot function in a vacuum. To make that processor work, we have to engineer an ecosystem around it by solving 3 specific architectural problems. We must provide regulated DC power, we must extract the resulting thermal load, and we must build pathways for parallel data delivery. We are going to build this system step by step from first principles. By observing how each component solves a specific physical limitation, we can see exactly how hardware is configured to prevent data bottlenecks. Before a single byte of data can be processed, we have to establish a thermodynamic baseline. That means our absolute first priority is securing strictly regulated electrical power. We shift our focus away from the bare motherboard and move to the power supply unit, or PSU. Looking at the rear of this power supply, you can see the main plug input and a red voltage switch for 115 or 230 volts. Wall outlets provide raw alternating current. If you delivered AC power directly to your delicate PC components, the voltage spikes would immediately destroy them. This interior view of an open power supply shows how the unit protects the system. It acts as a massive transformer and rectifier, passing the raw AC current through an EMI filter and a series of heavy-duty capacitors to flatten the electrical wave into stable direct current. Once rectified, the PSU splits that direct current into specific low-voltage outputs required by the motherboard and peripherals, specifically stepping it down to 3.3 volt, 5 volt, and 12 volt streams delivered through these 24-pin, 8-pin, and SATA connectors. To know exactly how large of a power supply we need, we calculate the total system demand using a strict mathematical formula. As shown here, total wattage is simply the required voltage multiplied by the current in amps drawn by every component combined. But the conversion from alternating to direct current is never perfect. Every power supply wastes a percentage of the electrical draw, and that wasted AC power is physically converted into heat. This is where the 80+ certification program applies. It classifies power supply efficiency on a spectrum from bronze to titanium. A titanium unit operates at over 90% efficiency, meaning very little energy is lost in the conversion. Low-efficiency, unrated power supplies draw excess current from the wall and dump that wasted energy directly into the computer chassis as a raw thermal load. Establishing regulated DC power solves the motherboard's electrical dependency, but in doing so, we've introduced a physical threat to the hardware. That heat has to go somewhere. We move our focus back to the CPU socket. Electricity is now flowing into the silicon, and that current is generating friction. Electrical resistance inevitably produces heat. If we leave the silicon exposed, the temperature will quickly breach the hardware's thermal limits. To survive, the CPU will drastically throttle its processing speed and then shut itself down entirely. This microscopic cross-section illustrates the problem. Even when you clamp a smooth metal heatsink directly onto the metal surface of the CPU, microscopic imperfections in both surfaces create tiny gaps.
These pockets trap air, and stagnant air is a highly effective thermal insulator. We solve this by applying thermal paste. The paste is a highly conductive compound that fills those microscopic imperfections, physically displacing the insulating air and creating a seamless bridge for the heat to move upward into the metal block. Once the heat is in the metal, it travels up into the heatsink's tightly packed fin arrays. These fins are designed to maximize surface area, allowing the attached fans to strip the heat away and exhaust it out of the chassis. For systems generating massive thermal loads, we can replace the air cooler with an open-loop liquid cooling system. This schematic maps the mechanical path. A pump drives fluid through a CPU water block where it absorbs the heat, then carries it away to a large radiator where fans expel it from the system. As a brief note, this thermodynamic extraction is highly dependent on clear physical space. Using a modular power supply allows you to remove unused cables from the case, ensuring fans have an unobstructed path to push the air out. With clean power flowing in and heat continually flowing out, the system is physically secure.
But the CPU will sit completely idle until we build a way to feed it parallel streams of data. Next, we look at the long, empty slots adjacent to the CPU socket. This is where system memory goes. Random access memory, or RAM, acts as the processor's active workspace. Every operation between the RAM and the CPU is dictated by the system clock wave, which acts as a metronome for the hardware. This animation shows the early standard, synchronous DRAM. Notice the timing. The data packet only pulses and transfers when the digital clock wave hits its rising peak. It moves data exactly once per cycle. To eliminate that limitation, engineers developed double data rate memory. By transmitting data on both the rising edge and the falling edge of the clock cycle, the throughput is instantly doubled without needing to increase the actual clock speed. However, even with double data rate memory, a single stick of RAM is physically constrained. It communicates with the processor over a single 64-bit data bus. We bypass this constraint by utilizing dual-channel architecture. By installing identical memory modules into specifically paired color-coded slots on the motherboard, we change how the processor interacts with the RAM. Watch the pipeline here. Instead of forcing the memory controller to handle two separate 64-bit streams, the dual-channel configuration links them into a single, unified 128-bit pathway. It effectively doubles the bandwidth directly to the CPU. That 128-bit pipeline is the consumer standard, but in enterprise servers, data volume is so high that mathematical errors inevitably occur within the memory cells themselves. To prevent those errors from crashing a server, enterprise motherboards require ECC, or Error Correction Code RAM. An ECC module includes an extra memory chip solely dedicated to detecting and mathematically repairing single-bit data errors on the fly. We have now established a massive, high-speed 128-bit pipeline directly into the processor. But RAM is volatile. It clears out when the power drops. To keep that pipeline fed, we need structured, persistent storage. We move away from the motherboard entirely, down into the chassis drive bays where the persistent storage lives. Historically, data was stored on hard disk drives, relying on mechanical, spinning magnetic plotters. Today, solid-state drives, utilizing static flash memory cells, offer significantly faster read and write performance. But regardless of whether you use an HDD or an SSD, relying on a single storage drive introduces a critical architectural flaw. A single drive has a hard limit on its data transfer speed, and worse, it acts as a single point of failure. If that one drive dies, all the data dies with it. We resolve both the speed bottleneck and the physical vulnerability by implementing a redundant array of independent disks, known as RAID. This diagram illustrates RAID 0, or striping. The data stream is broken into blocks and dealt alternately across two drives. Because two drives write simultaneously, performance is fast. But if either drive fails, the entire array is destroyed. There is zero fault tolerance. Conversely, this is RAID 1, or mirroring. The exact same data stream is cloned simultaneously to both drives. This perfectly protects your data if a drive physically dies, but it cuts your total usable storage capacity in half. To balance speed, capacity, and security, enterprise environments typically use RAID 5, which requires a minimum of 3 drives to operate. RAID 5 stripes data across the drives for speed, but it also calculates a mathematical parity block, distributing it across the array. As you see here, if one physical drive fails, the system uses that parity data to instantly reconstruct the missing information. For absolute maximum performance, systems can use RAID 10. This is a nested solution that takes the high-speed striping of a RAID 0 array and runs it across the perfectly cloned drives of a RAID 1 array. By parallelizing storage reads and writes via RAID, the storage bottleneck is mitigated, creating a more continuous, protected feed of data to the system memory. Pulling back, we can now view the fully populated system operating at peak capacity. The foundation holds firm. High-efficiency conversion delivers a perfectly flat, regulated 12-volt baseline to the board. The thermodynamic balance is maintained. Dense thermal bridges and massive fin arrays continuously extract the inevitable friction of the electrical current. And the data architecture flows freely. Fault-tolerant RAID arrays feed persistent data directly into wide 128-bit memory pipelines. The computer functions as an interdependent, engineered ecosystem. Peak performance is achieved only by resolving the specific bottlenecks across electricity, thermodynamics, and data pathways.